This is a voltaic cell, right, which is one of our types of electrochemical cells. So I'm just going to write that over here on the top of my screen that this is a voltaic cell. Why is there? Oops, here we go. Sorry about that. All right, so this is our voltaic cell and oh my goodness, cannot spell, can't spell. Let me erase and let me go and make sure that looks better. Okay. All right, so here we go. Come on, computer, behave. All right, so a voltaic cell. And I know it's a voltaic cell because I see a salt bridge and I see two electrodes and I see a wire and I see two aqueous solutions with an electrolyte. All right, so that's how I know it's a voltaic cell. And remember, a voltaic cell converts chemical energy into electrical energy. And so ELECT, electrical energy. All right. All right, so chemical energy to electrical energy. All right, so now let's just take a little look, and I'm just going to make this a little bit smaller so I can just get a better look over here and at the label. Actually, I think I liked it better at 125. Okay. So I can identify that my electrons are going to go through the wire, and I'm not going to state the direction yet. I'm just going to go my electrons through the wire, and I'm not sure why that just made that really weird line. All right. So my electrons going through the wire. Looks like my pen feels like being a little bit tricky today. All right, so I have the salt bridge, right? The salt bridge is where ions go through, right? Our ions are going to flow in and out of the salt bridge in order to maintain neutrality. There's a little bit of delay on the pen, but that's okay. All right, so let's take a look. We've got our liquid solutions, right? So that's our electrolyte, right? We need an electrolyte for those mobile ions, and that allows our electric current, right? Allows those electrons to flow as well. All right, so what we need to do is we need to elaborate and talk about the two electrodes that we have, right? We have an aluminum electrode and we have a lead electrode. One of them is the anode and one of them is the cathode. One of them gets oxidized and one of them gets reduced. So now the one that gets oxidized is the anode, right? So remember our little memory trick, we have an ox, right? And so an ox, an anorexic anox, so our anode is going to end up getting smaller. And now we have an ox and we have red cat. And our reduction will be at the cathode, fat red cat, so our cathode will get bigger. All right, so then we also have our memory trick of lose electrons oxidation, gain electrons reduction. So oxidation is where we lose electrons. So we lose electrons at the anode, and the electrons are going to go from the anode through the cathode through the wire. So now in order to figure out the anode, we need to identify which metal is higher up on table J. So we're comparing aluminum to lead. So aluminum is the higher metal on table J. So higher on table J. And lead is our lower metal on table J. And since aluminum is the higher metal is going to be oxidized. And what is our ox? That's our anox. So this is our anode. Right, so aluminum is our anode. And so now the lower metal is the one that gets reduced. So then this is going to be reduced, and reduction occurs at the cathode. Okay, and remember we have a fat red cat, so that means our cathode will be larger. And we have the anorexic ox, so our anode will get smaller. All right, let's take a look at some of those questions. But first, electrons go from the anode to the cathode. So our direction of electron flow in this case is going to be from aluminum through the voltmeter. Voltmeter is not a battery, it's just a measuring device that just measures the voltage across the wire. And so we're going to go in this direction, right? So our electron flow is from anode to cathode, and it's going to be from left to right in this case, or aluminum to lead. All right, so which one's more easily oxidized, the aluminum or the lead? Now that's going to be our aluminum, and the reason why is it is higher up on table J. So now we want the balanced equation showing the spontaneous reaction that occurs. And what is the maximum voltage? This, I do not have my honors reference table, so we're going to skip that question. All right, so aluminum is the most easily oxidized. And so we're going to show, I'm going to show the two half reactions here for question number 2. And we'll show that, and I'll just draw that on the diagram. But let's just take a look at the rest of our questions here. So we're going to hold off on question number 2 for just a second. And the direction of electron flow in the wire, you could say from left to right. It's not always going to be left to right. It just depends on which electrode they put in which beaker and which one they put on the left or the right. It all has to do that it always goes from the anode to the cathode. And then in this case, it is the aluminum anode to our lead cathode. So aluminum to lead. And what is the direction of the positive ion flow? Which electrode is decreasing inside? So I'm going to hold off the positive ion flow. I'm going to just skip over that for just a second. So it decreasing in size, right? So the anorexic ox, right? So then that's going to be the anode that will decrease in size. And then again, our anode was the aluminum electrode. And then increase in size, that cat. So then that is going to be our cathode. And that is going to be the lead. All right, so let's just take a look here and let's go to see what's going on with our electrons here. So anode oxidation, right? Ox, lose electrons. So lose electrons is oxidation. So now this aluminum is going to lose electrons, right? So this is an aluminum, right? That's 0. And then it's losing these electrons, right? Those are going up the wire. So then it forms aluminum ions. So it forms aqueous ions, right? So that's what's happening here. And so the reason why it gets smaller is because as those electrons get lost, right, the ions are soluble in the water in this aqueous solution. So that's why we end up with this +3 aluminum charge. So now, since we're increasing positive charge in this electrolyte, what's going to happen? We're going to have some negative ions, right? So we're going to have some negative ions are going to start kind of come out there to maintain neutrality. And so now let's see, we've got our electrons that go up through the wire. And now here we have where reduction occurs. So it's not this 0 lead here that's getting reduced. It's actually this lead that's getting reduced because this is where the electrons are gained. So then our electrons are coming into here, and then there's these lead that are +2, and I know that because each nitrate is -1 from table E. And so this +2 is going to gain electrons, right? So plus those 2 electrons, and then it's going to start building up on over here. All right, so then this is going to be then where our negative ions are going to, come out. Okay, so here we have, where did I want to write over here? I wanted to write something. I can't remember what I wanted to write. Oh, yes, it's larger. Oh, I already wrote that. So we're good. All right. So let's talk about the equation. So we have the aluminum starts off at 0. I'm going to write the half reactions. So aluminum starts off at 0. And aluminum goes to a +3. I know it's +3 because the periodic table, and also because each of these nitrates is -1. And I'm having lots of pen issues today. And so then that's going to be a +3. So +3 electrons. right? So far, so good. And that is supposed to say 3 electrons. All right, so then now we're going to do our reduction half reaction. So we have our lead, and our lead is starting off at +2, and it's going to gain 2 electrons, right? Because to balance off that nitrate, and go to 0. Okay, so now 3 electrons lost, 2 electrons gained, right? So then that means that we need to multiply each of our half reactions to balance for the number of electrons. So I have multiplied this one by 2 and this one by 3. So then my total electrons lost equal my electrons gained. And again, I don't know why I'm getting this weird line on my screen. So I apologize for that. Technology is not my thing. So then when I write the reaction, I'm going to have 2 aluminums plus 3 lead and that's going to make our 2 aluminums with a +3 plus our lead and right the 3 in front of the lead. All right, so that's going to be our overall reaction, which we get from our 2 half reactions by combining them. Okay, so then this would definitely be honors topic, as with number 3. Right, and you wouldn't be expected to do that on the Regents exam. All right, the direction of positive ion flow is going to be into the cathode side. All right, so I'm just going to write here towards the cathode side. All right. All right, so now what's happening to the concentration of aluminum ions? Okay, so the aluminum ions are increasing. Right, they're increasing because, right, those losing electrons, right? So the aluminum ions. So what's basically happening in terms of atoms and ions, atoms lose electrons to form ions, right? That's what's happening on the side that is oxidizing over there. And what's happening to our lead ions? Our lead ions are decreasing. And what's happening over there is the exact opposite. So instead of starting with ions, we're starting with, instead of starting with atoms, we're starting with ions, and then we're gain electrons, and then to form atoms. All right, sorry for the messy handwriting. And again, voltage, I would need the honors reference tables for that, so I'm going to skip that. All right, and then we've already identified our anode, in this case is aluminum. We've identified this as lead, right? We did that by using which reference table? I'm just going to write that over here. You're just going to use table J for that. And which is the positive electrode and which is the negative electrode. All right, so the anode is going to be negative. So our anode. And red cat, right? Think like a cat. Cats have paws, positive, right? So the cathode is positive. And again, we have our anode is the aluminum and the cathode is the lead. All right, so those are our different electrodes. Anode, again, I'm just going to throw anode oxidation, cathode reduction, right? Because we have an ox, red cat is fat, anox is anorexic or getting smaller. All right, so there we have everything you need to know and then some for our voltaic cells. And I know it seems like a lot is going on in this case. And the best thing to do is to practice using different electrodes and answer some questions. All right, good luck.